Yes. All right, very quickly. So what we're doing today, we're just looking at some examples here. A little review of linear functions. Okay. How we graph them, how we manipulate them, etc. Okay. So linear relations, what do we know about linear relations? When points on a graph lie in a straight line, then that's what we call linear relation, right? So if they're all the points are collinear, they lie on the same line, then it's a linear relation. We can always write linear relations in terms of a linear equation. Does the linear equation have to be a function? I mean, it seems like if you think about almost every case it would, but there's one type of a line where it wouldn't be. What would that be? Are you doing this for the line?
Yeah.
I couldn't tell. A vertical line, right? Obviously, that's the one case where you'd have a vertical line wouldn't be considered a function. But every line that's non-vertical would be a function because it would pass the vertical line test. Vertical line obviously fails the vertical line test. So there are many ways that we can write linear relations, and most of the time linear functions. We'll just say linear equations, right? Why do we write them in different forms? Well, it depends what we want to do with them. Most of the time, probably you've written linear equations in what form? So y equals mx plus b, which, what do we call that? Slope intercept, yeah. Where m's the slope, b is the y-intercept. This is all going to be old hat work. You've done a lot of this stuff. Okay, sometimes though, we don't want to write them that way. Like when we're dealing with linear equations, now this is going to sound weird to you, but we can have linear equations that, we're not going to talk about them today, but we can have linear equations with more than two variables too, right? That would represent something different than what you're used to. When we talk about linear equations in two variables, the graphs always look like lines. But when we talk about linear equations in higher dimensions, linear equations that involve more than two dimensions, what does it mean to be linear? It means that it follows the same kind of pattern as a linear equation in two variables, only it has more, right? Now, what do you suppose, I'll hold off on this. This will be kind of a fun way to end the conversation today, but we'll look at some examples of what happens when you add another variable to the x and y to the mix, okay? But just suffice it to say for now, there are times when we definitely would prefer to write our linear equations in what's called standard form. Okay, do you remember standard form? Yeah, good. It's the ax plus by equals c form, right? Is that what you're thinking of? Yeah, and you probably haven't done a lot in standard form. You probably maybe just touched on that briefly in Algebra 1, but you may or may not have done an awful lot with it. And certainly you probably wouldn't have had a strong idea why you're doing it at that point. This will be the first year where it'll kind of make sense. One place where it's going to be particularly useful is when we develop matrices for solving systems, big systems, which is coming up here pretty soon, within next week and a half or so. And then we definitely need to write all the linear equations in standard form. So what's it mean to be written in standard form? Standard form is just this form. If I'm using the variables x and y, it would look like ax plus by equals c. Okay, but there are some criteria that we need to apply to the coefficients a, b, and c. Right? When I say coefficient, what do I mean? What's a coefficient in math?
It's your,
Say it again. Okay, it's a number that's being multiplied by a variable, a coefficient, right? So we'd say that a is the coefficient of x and b is the coefficient of y here, right? C is what we call the constant. So a, b, and c have to be integers, and they can't be fractions. And here's another one that sometimes people get lazy on, but it's technically true. A needs to be greater than or equal to 1, so a shouldn't be negative if we're writing it in standard form, okay? So the other thing that would need to be true is that the greatest common factor of a, b, and c is 1, right? So if there's a common factor bigger than 1 of a, b, and c, then we would just divide both sides of the equation by that common factor and make those numbers a little bit smaller and simpler, right? Okay, so let's first of all just practice putting some equations into standard form. It's easy to do, right? What about equation 1 here? It's close to standard form. What's the only problem?
A is
A is negative, yeah. So what do I do? Divide by -1, same thing as multiplying by -1. I'm just going to change all the signs, right? So that one's just going to become a positive 5x, a negative 6y, and a positive 12. And now it's in standard form. Easy. Okay, what about this guy right here?
plus 24.
What about this guy right here? What would we have to do? Subtract the 2x maybe to the other side, and then I'm going to divide or multiply by -1 to flip all the signs, which is going to give me positive 2x minus y equals positive 9. Okay? What about something like this? It's almost in the x's and y terms are in the right places, but I don't have integers.
Multiply by 12.
Multiply by 12. Good, I'm going to clear the fractions, just like we've been doing, right? So here's one where I'm going to write it down here so I can write it a little bigger. We'll distribute a 12 through both sides. And so we can, remember when we're clearing fractions, we'd always simplify first, we'll reduce first, and then multiply by the numerator, right? It's a lot easier that way. So 4 goes into 12 how many times? So what do we end up with on top? Good, 9x. 3 goes into 12. So I get a minus 4y, and then over here I just get a 12. Right? Okay, no big deal. You guys have got that stuff. And then same kind of thing over here. In this case, I would just distribute a 6 through both sides. Everybody agree?
Yeah.
And then if I distribute a 6 through, I'm going to get an x. I'm going to get a 6y. And I'm going to get, a minus 12. So I'll just add the 6y, or I'll subtract the 6y to the other side. Okay, no big deal.
Wait, on that one, why is it negative?
Because I'm distributing the 6 to a y minus 2.
So it can stay negative?
Well, yeah, it will, right? Because I'm gonna end up, when I distribute the 6 on the left side, I'm just gonna get an x. When I distribute the 6 on the right side of the equation, I'm gonna get a 6y minus 12, right? Does that make sense? Does that make sense? Yeah, right. The only term that has to be positive is a. The only coefficient that has to be positive. Yes, Eric.
So on 4, you get 7x plus 7y equals 7. Do you have to simplify that down?
You would, right. So that's a good one to look at too. So if I add the 7x to this side, everybody agree we're going to get 7x plus 7y equals 7, right?
Yeah.
Okay, so then I could divide everything by 7 and make that look simpler. Divide, because 7 is a common factor. So if I divide the whole thing, both sides, by 7, I just get x plus y equals 1. Make sense? Okay? All right. So then, the form that you're more familiar with is slope-intercept form. Right? So slope-intercept form is, you guys already told me what that is, right? Slope-intercept form. Yeah, y equals mx plus b, and you're real familiar with that. And, they've got this written down. You rarely ever write it this way, but you could, if it's a function, you could trade the y for an f of x. If it's a linear function, we could write it using function notation. But really, this is, this is how we, that's fine. That's how you're used to it, it's fine. So m is the slope, you told me, right? And b is the what? Okay, so slope is the rate of change, constant rate of change between the points, and we all know that's just rise over run. And you guys are familiar with that, I'm sure. So what about the different types of slopes? Let's just focus on that. So we could say, if we wanted to, we could divide the slope up into 4 broad categories. Okay? So what if we talked about, for example, a positive slope? What's that telling me? And And that's kind of an important, simple but important concept. The line has a positive slope, say it again. It's gonna go up from left to right, right? As we move in the positive x direction. So as an ant walks from left to right on the function, he's always going uphill, right? So that would be something like this. So there's an example of a line with positive slope, right? Then by the same token, what would negative be? Okay, good. So an ant moving in the positive x direction from left to right would be going, walking downhill, no big deal. And then the other two, what's a zero slope look like? It's flat, horizontal, flat, or vertical?
Horizontal.
Horizontal, right? And that makes sense, doesn't it? Because if slope is rise over run, if I take any 2 points, so here's an example of a line with zero slope. If I pick any 2 points on the line and I calculate rise over run, well, the run could be some distance, but what's the rise always going to be on a horizontal line? Zero, which makes sense because 0 divided by 9 is 0, right? So that makes sense. And then the other one is undefined.
Which is a vertical.
Right. Undefined would be, and you probably remember this, that's, undefined is a vertical line.
I think we need an explanation of what Tatum just said.
Ask her.
Say it again.
What is a suicide
Okay, all right. I don't think that's a mathematical explanation, but I'll take it. So why is it, can someone articulate a little way to justify why we say it's undefined? What do you think? Oh, okay, I think you guys are kind of going in the same direction with that. If I take any 2 points on a vertical line, I can define a rise, right? But the run is always going to be 0. And can I divide by 0?
No.
It's against the rules, right? That's one of our 2 rules for real numbers. We can't divide by 0, and so therefore we can't define a number for it, so it's undefined. Right, there's no, we can get 0 on the bottom of our slope practice. Okay, so then a little bit of practice, and this is easy stuff. I know you've done a lot of this. Consider this kind of just warm up, I guess, for stuff we're going to be doing soon.
Guys. Andrew.
Okay, so when we're graphing lines, one way, there's several approaches we can use to graphing lines. It's always going to be easy. Our strategy is always going to be the same when we're sketching graphs of lines. We're always going to start with an anchor point. We're going to create a second point, and we connect and extend. That probably sounds familiar, right? So all it takes 2 points to define a line. You don't need any more than 2. 2 points defines a line completely, right? Yeah, you don't need to. You don't need to. All you need, and that's just redundant, kind of waste of time. You only need 2 points to define a line. So you're going to pick 2 convenient points. How do we do that? Well, one way we can do that is we can put the function into slope-intercept form. If I've got a function written in slope-intercept form, what would my 2 points be that I would use? Like, let's take this as an example right here. Y equals 2/5 x plus 7. Where would my I might call it the anchor point. The first point we would choose would be 0, 7, right? We know that the y-intercept is b, and b is equal to 7. So we'd go to the point 0, 7, 0, 1, 2, 3, 4, 5, 6, 7, right there. And there's 1 point. Okay? Now from that point, how could I get a second point? What do you think, Maria?
Down to the left 5.
Okay, so we're going to use a slope triangle, aren't we? We know that the rise over run, the slope is 2/5. So that tells me that I would either rise by 2 and run by 5. 1, 2, 3, 4, 5, run to there. That's not very convenient on our graph. So I could just reverse both of those, wouldn't I? I could also say, okay, I'll do the opposite. I could rise by -2 and run by -5. Either way, I'm going to get a second point that I need. So down to 1, 2, 3, 4, 5 puts me me right there. And now all I have to do is just connect and extend, and I've got my line. Okay, no big deal. And that's, I know you've done that a million times. So what about for a problem like number 9 then? How could I use that strategy on number 9?
Well, negative slope.
Okay, good. I can isolate the y. And we've already done a bunch of algebra already this year where we practiced those skills sort of in a vacuum without a purpose. But now we have a purpose. I could just isolate the y. That's really just solving a literal equation, solving one variable in terms of another one, right? If I isolate y, I expect to get x's in my answer. By isolating y and simplifying, aren't I inevitably always going to end up in slope-intercept form? Right? That's really what I do, okay? So for this example here, we would just subtract the x from both sides, divide both sides by 3, which is the same as multiplying both sides by 1/3, right? On the right side, I get a y, because I canceled the 3. On the left side, I'm going to get negative x over 3, which is negative 1/3 x, minus 15 over 3, which is minus 5. Easy, right? Easy algebra. But what that points out then, it tells us that the slope is negative 1/3, and the y-intercept is negative 5, which makes graphing this a breeze, right? Now I just create my 2 points and connect and extend. There's the y-intercept, 0, 5. I'm going to make a slope triangle where I'm going to go from that point, I go down by 1 and over by 3 and create another point and connect and extend, and we got it. So that's one strategy. You can always take a linear equation and put it into slope-intercept form by isolating y and use the y-intercept and the slope to quickly sketch the graph, okay? Yes, we probably can skip that example. You can guess that. Okay, what about horizontal and vertical lines? What's the equation of this line right here? X equals negative 3. It's hard to see this, it's all in black. How about if I do this?
And y equals.
Okay, X equals negative 3. And then over here we get y equals 1. Okay? You got it, you remembered that. Now justify it. Why does that make sense? Why does x equal negative 3 make sense in a mathematical way? It's more than just memorizing a fact here. It's actually the only way we could do this. Why does that make so much sense? Okay, so it goes through the x-axis. That's a great way to remember it. So it intersects the x-axis at the x-intercept, negative 3.
And there's
Okay.
no y-intercept.
And there's no y-intercept, okay? And by the same token, y only intersects the y-axis, and it intersects the y-axis at the y-intercept of 1. I think you could even go deeper than that, though, okay? Does this line right here depend on, well,
Y, how x is.
yeah. Are y and x connected in any important way here?
No,
No.
because there's no rise over run.
There's no rise over run, but for every point, if I just pick a bunch of random points on this curve, what are the coordinates of this point right here?
Something negative 4, negative 3.
I get, would you agree that I get negative 3,
Oh, negative 4.
negative 4? How about that point right there?
Negative 3, 4.
I could do this all day. What's going to be the same each time?
X-axis.
The x coordinate's the same every time, isn't it, right? So y could be, there is no restriction on what y could be, right? I can guarantee that I'm going to get a point on the line if I just say, I'm going to take the point negative 3, whatever. It's a point on the line. We can indiscriminately pick a value of y, makes no difference. But x is specific. X always has to be negative 3. So this is something, you're going to see this trend in math, and this is kind of a higher concept here. If we've got a relationship here that is completely independent of the value of y, why would the y show up in the equation? There's no need, right? It's the whole relationship here, the equation should be transparent to the value of y, because y can be anything indiscriminately. The only thing that's important here that's specific is the x value. Okay, does that make sense? By the same token, here, all that's important is the y value. X could be anything, doesn't matter. No matter what x is, the y is always equal to 1. Question? The rise over run on number 11? Yeah, so if we tried to calculate a slope on that for number 11, slope is rise over run, isn't it? So if we pick these 2 points, for example, well, the rise would be 8. What's the run?
0.
0, right? Because I'm not moving horizontally, and that's a problem, isn't it? Right?
I mean, it's true.
So that's why we can't define a slope for that, because you can't divide by 0. Okay? Good question. Did you see how that's different, though? I just want to go back to one of these previous examples. I want to make sure you guys get what I'm saying with this. You see how that's different than, for example, this one right here? I have to have both the x and the y in my equation, because this time, if I pick an x value of, let's say, 10, right? If I pick an x value of 10, the y value is predetermined by the x value. They're linked. I have to have both variables in there, because when I pick an x value, there's only one specific y value that's going to go with that, and vice versa. If I pick a y value, there's only one x value that can go with that, and what determines what those values are? This rule right here that we call an equation, right? See, that's a different relationship. Okay, so what can you tell me about slopes of parallel lines versus perpendicular lines? Slopes of parallel lines are what? Yeah, they'd have to be equal, wouldn't they? Right? Whoops. So slopes of parallel lines are equal. And what about the slopes of perpendicular lines? Yeah, so if you guaranteed if the slopes are equal of 2 lines, guaranteed the lines are parallel, right? They have to be. What about perpendicular though? Do you remember that relationship?
They never touch.
Slopes never touch, right?
Are they
I mean,
equal to zero?
parallel lines never touch. Perpendicular lines cross at a right angle, right?
They're the exact opposite.
Well, it's more than just opposites. They are opposite in sign. So if one's positive, the other one's negative. But there's another part of that relationship.
Oh.
You don't remember?
Are they equal to 0?
There it is, negative reciprocals. Okay, so the slopes of perpendicular lines are negative reciprocals every time. Okay, so another way of thinking about that, if I take negative reciprocals and I multiply them together, what's going to happen? And let's just take a random example. I don't want to take something specific. Let's be totally general. Let's say the slope of line 1 is, say, a over b, right? What's the only thing that has to be true there? Well, b can't equal 0, right? That make sense? So then,
So if b were equal to 0, that would be an undefined.
yeah, if b were equal to 0, then that would be a vertical line,
Okay.
right? Okay. So how about let's just say we're going to get the line 2 is perpendicular to line 1. Well, you already told me that if they're perpendicular, they are negative reciprocals. So I multiply by -1 and I flip the fraction. And I guess we also know here that a can't equal 0, right? That makes sense. What kind of a line would be perpendicular to a horizontal line? If the slope of one line were 0, it'd be vertical, right? So that would create a problem for I'd have an undefined slope for the other line. But let's take examples that are, that aren't that simple, where the line actually has some non-zero slope to it, okay? What if I take the product of those two slopes? Look what happens. This is kind of interesting. I get a over b times negative b over a. So what happens?
They go like,
Everything cross cancels, and I get 1 times -1 is -1. So the products of the slopes of perpendicular lines is always -1. Okay? And that's That's profound at a level we can't really get to yet, but that has a lot to do with, if we're gonna extend our discussion of linear equations to higher dimensions, that tells us something kind of important about what happens when you take products of these slopes, or products of certain properties of linear functions, even if they're higher dimensional functions. Okay, so how do we determine whether a pair of lines is parallel, perpendicular, or neither? Simple, what do we do? Find M. Yeah, find M. And we can do that by isolating y and putting it in slope-intercept form. That's one way to do it. But somehow we gotta find the slopes, and if the slopes are equal, they're parallel. If they're opposite reciprocals, they're perpendicular. And if neither of those things are true, what's the relationship? Neither. They're neither perpendicular nor parallel, right? So let's look at just a couple of quick examples of this. So what about these two here? If I solve for y in this first one, right? If I isolate the y, I could just, I could multiply each side by -1 to make the, but what did I do? No, I didn't. What did I do? I just added 8x to the other side. Duh. Added 8x, and I divided by 8, and I get y equals x. So the slope is 1. How about this guy? I subtracted the x, I multiplied by -1, and I get m equals 1. So those are parallel lines for sure, right? Because they have the same slopes. How about something like this here? What are we going to do? We're just going to subtract the 9x to the other side, divide each side by -6. So -9 over -6 reduces to 3/2. -20 divided by -6 reduces to 10/3. I don't really care about that though, do I? In this case, all I care about is the coefficient of x. I didn't even really have to do that work, right? I knew right away that the slope was 3/2. How about over here? I'm going to divide each side by -3. And so I'm going to get y equals 2 divided by -3. Stop. That's all I need, right? -2/3 and +3/2 are opposite reciprocals, and so they're perpendicular. I don't really care about the y-intercept. If all I'm asked to find is what's their slope relationship, right? Okay, last part. Finding x and y intercepts. What are we at here, 10?
Yeah.
Okay, we'll be finished. So finding x and y intercepts. This is, now if you think about this at a kind of a conceptual level, it's super easy stuff, right? Don't remember this stuff as a fact because you'll just forget it. So we already know what the definitions are. An x-intercept is where a graph crosses the x-axis. A y-intercept is where it crosses the y-axis. What's significant about every x-intercept? It's where it crosses the x-axis, but what can you tell me about any x-intercept? They all have something in common.
They all intercept x.
Say it again. Crosses the x-axis. So what can you tell me about, let's say, the coordinates that represent those points? Say it again. True, but what's every x-intercept, if I write it as an ordered pair, is going to have one of those coordinates is going to be the same. Y is 0 every time, right? Does that make sense? If it's on the x-axis, y is 0. So if I want to do something like I want to find an example, like right here, let's say. If I want to find the x-intercept, then what would I do to this equation to find the x-intercept? You told me it's where the y-coordinate is 0, right? Okay, so think about this algebraically then. If I wanted to find the x-intercept, I'm going to choose the ordered pair where I know x is 0. How am I going to find the corresponding y? Well, I could, but let's say we don't have graphing technology available. We want to just do this algebraically. There's the equation that defines the line. Well, not necessarily. That's the y-intercept, right? We're looking for the x-intercept. What could I think I heard it. Plug it in, right? If we want to know this, the way you ask the math gods where the x-intercept is you say, okay, where does x equal 0? Or we're looking for x-intercept, aren't we?
So would it be -1?
I got that backwards. So the x-intercept, you already told me that's where y equals 0, right? Okay? So all I've got to do is I'm just going to evaluate this function when y equals 0. So I get the equation 0 equals 5x minus 1. That equation that's the way the math gods give me an answer. If I want to know where the x-intercept is, I set y equal to 0, and I get the answer through algebra. What are the 2 steps to isolate x?
Add one.
1 divided by
Divide by 5. So when x is 0, or when y is 0, sorry, x has to be 1/5. So there's my x-intercept. Now, by the same logic, the y-intercept is where x is 0, right? If we have a line that's written in slope-intercept form, we already know the answer is going to be -1, don't we? But we can see that algebraically pretty easily, right? I could do the same kind of thinking. If I'm looking for the y-intercept, that's going to be where x is 0. Well, when x is 0, what happens to my equation? I get y equals 5 times 0 minus 1. 5 times 0 is just 0, right? So we're able to use what's called the cover-up technique here. Because I've got 5 times x, when I let x equal 0, I can just cover up that term because it goes away and solve the remaining equation, which is already solved. Y equals -1, right? Okay, now why is that useful? We said earlier, and there's why I'm going to close this down, and we'll wrap this up later. But how many points does it take to define a line? 2. There's 2 points, right? I've got the intercepts. I've got the point 0, -1, and the point 1/5, 0, which is kind of hard to graph. But there's my line. Make sense? Okay, good.